Good afternoon. My name is Johnny Nelson, and I will be reviewing the concept of surface integrity in machining or material removal operations. In applications, I always like to start out with applications since it gives us a little bit of context, why we should pay attention and why we should care. But even before that, the philosophy or the concept of surface integrity intrigued me as I was reading through some literature on different tribological properties, functions, and whatnot. It's of main concern in critical applications, since those type of applications often have difficult to machine materials. So surface integrity is necessary for most applications that we machine or that a company machines or manufactures, but it's especially critical in, again, these critical applications such as gas turbines, auxiliary power units for aircraft, bearings, brakes, landing gears, dies and molds. Of course, we'll use different materials for these different applications, but again, it's that surface integrity that we're focusing on right now. A little bit of historical perspective. A gentleman in the 50s, Eric K. Henriksen was his name. He was the first one to, I'm sure there were others too, but he was the first one to approach it from an engineering / scientific standpoint, and look at what the machining or how the machining affected the material property or the surface property, and if that could be changed or modified, and if what effect that had on the long-term life of the component. He realized that the shearing effect causes the bending, and that of course causes hardening and other different things. So if that, obviously just using basic engineering principles, that obviously could be modified. Following this, in the 1960s through the 70s, there's a couple of researchers, Fields and Kales. They were the first one to introduce or coin the concept or the term of surface integrity, and they defined it as the inherent or enhanced condition of a surface produced in machining or other surface generation operation. Following that, in the 80s, their groundbreaking research, essentially, the American National Standard Institute created a standard on surface integrity. Also, in the 80s, a couple of American universities, noticeably Purdue and a couple of North Carolinian institutions, focused heavily in the surface integrity research area, especially focusing on gas turbines. Today, if you look through the literature, there's a vast amount of literature, and many researchers around the world, depending on their application or what they're researching and the application they're trying to research is, it's very, very broad and interesting. Fields and Kales, again, they were the first one to categorize this, taking it from Henriksen, and you can see in the left-hand column there we have the minimum surface integrity data set. Things like surface finish, macrostructure, no magnification less than 10 times, macro cracks, macro etch indications. So obviously just looking at it with the naked eye, you can see something is visibly wrong. And even within the data set, the minimum data set, they look at the microstructure too. So we have micro cracks, plastic deformation, phase transformations, intergranular attacks, pits, tears, laps, protrusions, and other abnormalities that the machining operation might cause. And then we jump to the middle column there, and we have, of course, it includes the minimum surface integrity data set, and then we also include fatigue tests or screening of the material, and stress corrosion tests, and also residual stress and distortions. So we're looking at those other parameters. And then finally, on the right-hand column, we have the extended SI data set. So that includes the standard SI data set, which includes the minimum SI data set. And going further, we have it often will include fatigue tests additional mechanical tests, tensile tests, stress rupture, creep, or other application-specific tests. These materials are often very tough, very hard, and they're going in demanding high-performance applications. So the researcher, engineer has to look at where those materials are being applied and look at those particular criteria. Now we delve into some details. Generally, like I mentioned at the beginning, these materials are difficult to machine. Normally they're referred to as super alloys, and they include things like stainless steel, nickel, and titanium alloys, or even high-strength steel. These all need higher cutting energy, they take a lot of deformation energy to cut. They're naturally very tough and have a high fracture strain. Most of the energy used to cut these materials is converted to heat. This is not rocket science, but just we're going through the basic details here. The heat is generated by the plastic deformation and the friction of the tool chip and tool workpiece interfaces. Another strike or blow against these materials is their low thermal conductivity. So you have this takes this massive amount of energy to cut, but then also coupled with this low thermal conductivity, you can see they're about 30% of plain carbon steel, and we have a lot of localized heating. So the deformation, if it heats up and the subsurface or the surrounding area does not heat up, we have a lot of deformation will stay in the material, and then resulting in residual stress. It could either be tensile or compressive. Possible problems of these things, obviously the residual stress staying in the material, that could be a problem too, is surface tearing, cavities, cracking, plastic deformation, or even increased surface roughness. There's been some instances measuring after they cut with particular tools, and especially titanium seem to have this problem, and we end up with very high residual stresses, even upwards of 1,000 megapascals. Here is an example of the difference between a regular steel and a stainless steel. We have on the left we have 316 stainless, and on the right we have 1045, and they just measure it with a infrared thermometer essentially. So we have an average chip surface there of around 600 centigrade, and on the right looks like maybe we have an average of 400. The cutting parameters were identical, same speed and feed rate, the same tool, the same machine, and you can see the increased energy that was inserted essentially to cut the stainless versus the regular steel. So that ties it back to our previous discussion of how you have to have, it takes a lot of energy to cut and deform these materials, and consequently a lot of heating takes place. Here's another example. We have in the red on the graph there, we have some 316 stainless. Again, in the green is the 1045, identical cutting tools and feed and speed rates. And the point of this graph, or what we're looking at, is essentially we have the residual stress that's changing, as you can see there. We have very high stress at the beginning for both, but particularly for the stainless. And then it dips way down and comes back up. The point is here we have this fairly substantial change in stress levels depending on the surface, as we go down into the surface into the subsurface. So with the steel, yes, it starts out a pretty high stress, but it levels out fairly quickly to basically a straight curve. Versus we have a well essentially around maybe 75 millimeters in the stainless, and then it comes back up to quite a bit less at the surface. So just that difference between the subsurface and the surface inherently leads to, as we've been discussing, problems in the material, residual compressive stresses, and this can just lead to a lot of problems versus the fairly straight curve of the regular steel. Here's another example. This one is, the point of this is showing the difference in exactly the same material, only the difference in cutting it. So again, we're looking for a straight curve. We don't want the gradient, a stress gradient in material if possible, between the surface and the subsurface. So we can see in the axial mode of cutting, it spikes pretty high at the surface, but then it drops to a fairly nominal level, and the curve is quite straight. The circumferential style of cutting, it's not a dramatic or a really steep curve, but it's still a curve, and there's a difference of between around 100 megapascals from the surface to about 1.6 millimeters into the surface. So just the way that you cut the material has a critical, or can have a critical effect on the component, the workpiece. So again, we're tying back into the tribological studies of surface integrity and how you get, and obviously you have to have a solid subsurface to have a good surface, and all these different factors can affect how the surface and the subsurface work together, and the longevity ultimately, and the quality of your piece that you're manufacturing. Our last example here, we have coated versus uncoated carbides, and my main research paper was discussing, they were manufacturing turbine blades and doing the final finish, and the coated are cheaper and they're longer lasting. However, they were introducing such high tensile residual stresses into the material that it was nearly twice, surprisingly enough, of what the uncoated cemented carbide tools. So if we jump back to our examples, we have the kind of material to show that it can have a dramatic effect. We have the type of cutting, the axial versus circumferential, and then finally we have the kind of tool. These small changes can have a dramatic effect on the way the surface or the material responds. So we have uncoated cemented carbide versus coated, and this can have there's many instances of having twice the residual stresses in the surface versus the subsurface. So again, that ties back to our main concept of that surface integrity. So that concludes my presentation. If you have any questions, please submit via email to the email address below. And then we have our references. Thank you for watching.